My name's Evan Olson, and I'll be solving problem 8.30 of the Fundamentals of Heat and Mass Transfer, 8th edition. For our problem statement, we have dry compressed air at 55 degrees Celsius and 15 atmospheres with a mass flow rate of 0.05 kilograms per second is entering a 50 millimeter diameter, 2.5 meter long tube whose surface temperature is 25 Celsius. We need to find the mean temperature of the air at the tube outlet and the rate of heat transfer from the air to the tube wall, as well as the power required to flow the air through the tube. Starting off with that, we have our schematic for the system. From the problem statement, we just have a simple tube with air flowing on the inside with our given parameters and a surface temperature of the tube for 25 degrees Celsius. It has a diameter of 50 millimeters and a length of 2.5 meters. We first need to determine whether it's turbulent or laminar flow. Um, we evaluate all of our properties of our fluid, which is air, at our film temperature, which is the average temperature between our bulk fluid temperature and the surface temperature of the fluid. So that will be 55 plus 25 degrees Celsius over 2, which turns out to be 40 degrees Celsius. And so you can determine the properties of air at 40 degrees Celsius as well as 15 atmospheres, since that's going to change the fluid properties a lot, especially for air, um, which are all of these values here, all of which will be important for this problem. We can calculate our Reynolds number using rho times u infinity times the diameter of our pipe, which is our characteristic length here, and dividing that by our dynamic viscosity. And since the free stream velocity was not given here, we can calculate it using m dot over our density times our area. And area is just pi r squared. It's the cross-sectional area of the pipe. That turns out to be around 1.5 meters per second. And when we plug that into our Reynolds number, it turns out to be 66,000, which is much greater than our critical Reynolds number for internal flow in a pipe of 2,300. And so we can assume that is turbulent flow here. To define to find the developing length and determine whether or not we need to, or what relationships we need to use for the heat transfer. Uh, for turbulent flow in a pipe, the fully developed length for hydraulic and thermodynamically developed fluids is going to be 10 times the diameter, which in this problem, the diameter is 50 millimeters. So that will turn out to be half a meter, which is 20% of our tube length. I went and assumed that it's fully developed for a majority of the tube, and so it's not going to result in that much different of an answer if you just assume that it's fully developed. And so that gives us a Nusselt number correlation here, which is 0.023 times our Reynolds number to the 0.8 power times our Prandtl number to the 0.4 power. If you evaluate that using our fluid properties or our Prandtl number and the Reynolds number we calculated, we get 144.92. And we can plug that into our equation for our heat transfer coefficient, which turns out to be around 80.5 watts per meter squared Kelvin. Now we can solve for our outlet temperature of the pipe using the log mean temperature difference method. In the log mean temperature difference is going to be given by this equation here for internal flow. And we can plug that into our relationship for our heat rate due to convection, which is equal to HA delta T log mean. And we also know that the heat stored within the fluid is going to be m dot times Cp delta T, and that will be delta T between the inlet and the outlet of the pipe. And so we can equate these two together, and then we can solve for our average temperature at the outlet. And I used MATLAB symbolic for this for ease of calculation. And if you plug in all of your known values, so we know the temperature at the inlet, the surface temperature of the pipe, and we know all of these values over here, we can just solve for this TMO, which occurs right here, and right here, and we get a temperature of around 41.23 degrees Celsius. And our heat transfer rate is simply defined as we used it in this log mean temperature difference equation of m dot Cp delta T, and that's delta T of the inlet minus the outlet, and we get around 709.34 watts. And we can calculate the power required to flow this much mass flow through our pipe just using standard pressure drop equation. And it's going to be the pressure drop which is causing any resistance to the flow due to any surface smoothness fluctuations. And so we know that the power required is going to be m dot times delta P over our density. And we know that our delta P, or our pressure drop, is going to be just due to major and minor head losses. So that's our friction coefficient times L over D times our rho U squared, which is our free stream velocity, divided by 2. And for smooth pipes given by the textbook, the friction coefficient can be estimated by 0.079 times Reynolds number to the minus 1/4 power. And so if we plug in all the values that we know from solving this problem, we get a power requirement of 13.9 milliwatts to flow 0.050 kilograms per second through this pipe. And for part B, it says, in an effort to reduce the capital cost of the installation, it's proposed to use a smaller 40 millimeter diameter tube, and we need to determine the required tube length and the required power for the smaller tube in order to achieve the same heat transfer rate for the larger tube. So to do this, we can go through the same exact process to determine our Reynolds number for the smaller pipe flow now. We get a Reynolds number of 8.34 times 10 to the 4. So it's still turbulent. Good. That's good news. And we can plug that into our Nusselt number correlation for the same fluid properties since no temperatures changed. And we get a heat transfer coefficient of 120.41, and that's solely increased due to our increased Reynolds number due to the smaller pipe diameter. And now we need to find the length of tube to give us the same heat transfer rate due to convection. And that's going to be equal to our convection coefficient times our area times our delta T log mean. And that has to be equal to the same exact heat transfer rate we calculated before. And since we know that the temperatures aren't changing in this scenario, our delta T log mean is going to stay exactly the same. And this is what's defining that here. We know that m dot is the same, Cp is the same, and our inlet and outlet temperatures are going to be the same. And so we can assume that our log mean temperature is the same, which this is the log mean temperature that was calculated in part A. And so now we can go back to this equation down here, plug in A and delta T log mean, and our area is just our circumference times our length, and we're trying to solve for length. So if we rearrange this solve for L, we get around 2.09 meters instead of 2.5 meters. And similarly, the power required to flow the fluid through this diameter pipe through this length is going to be the same exact equation. You can estimate the frictional factor using the same exact equation, and you get a uh, power requirement of 3.36 times 10 to the minus 2 watts.